Yeah, so good morning and welcome to Caltech. And we have a nice turnout today. I'm very pleased about that. So as Michelle just said, this week we have a workshop that we've been planning now for about 9 months. And the title of it is Optical Frequency Combs for Space Applications. Our first speaker this morning, who I'll introduce in just a moment, will be giving us really a tutorial on what is a frequency comb. So I think about a third of you in the audience are very familiar with frequency combs. Our workshop has been planned that way, but there are quite a few of you that might be coming more from the application side, and we'll have some tutorials later in the morning that you'll probably be very familiar to you. But the idea of this workshop, of which this short course is kind of the kickoff, is to bring together two very different communities. The community of specialists that are studying frequency combs, and really from the device side, the manufacturing side, and the physics side and the science side, and to mingle that community together with the applications community that could potentially benefit from some of the remarkable properties of combs. So many of you probably are familiar with some of the things that have happened with combs in the last 15 years, but there really are some truly remarkable metrology applications in other areas we'll hear about this morning that are completely new and have opened up because of the properties of combs. And so in the afternoon, we'll be sort of beginning to focus on the workshop part of it. But this morning, I want all of you to sit back and enjoy and learn a little bit about some areas, hopefully, that you know will be new to you. And so with that, kind of a little bit of background, I want to introduce our first speaker, Scott Diddams. We're very fortunate to have Scott involved both in the organization of the workshop, but also as a speaker. I really can't think of anyone who is, would know more about frequency combs in terms of giving a great tutorial than Scott. He has literally been involved in the subject from the very, very beginning. Back 15, 16 years ago, he was involved in the team at GILA and NIST that actually built the first self-reference frequency comb, and then has been involved at GILA in many, many applications. He was involved in the first demonstration with mercury ion clock, which is the ion clocks using combs are going to be the next time standard, and applications to microwaves. The most stable microwave synthesizers are now based on combs. Astrocombs, he's done it all. And so we're really very happy that he's here with us today. Just mention a few of the awards that Scott has received over the years. Okay, so he is the recipient of the Department of Commerce gold and silver medals for revolutionizing the way frequency is measured. He was a Presidential Career Award, or Early Career Award in Science and Engineering, the PCASE Awards, for work on frequency combs. He's a fellow of the Optical Society and the American Physical Society, and in addition to being a fellow at NIST and also leading the optical frequency measurements group there, he also holds a joint professorship at the University of Colorado. And so please, let's give Scott a very warm welcome.
Thank you very much, Kerry, for the kind words. So yeah, it's a real pleasure to be here and to share with you a little bit about frequency combs and kind of a big picture. Like Kerry mentioned, this morning session is going to be aimed on trying to get people to understand a common language. And so the presentation I will make today is tutorial in nature. So those of you who are also experts or already experts in frequency combs, I'd ask you to help me try to think about these things in a new way, particularly for applications that might make use of them. So for those of you who don't know anything about frequency combs or are new to the subject, feel free to, if you got a question in the middle that's just burning to ask, say it. Let's talk now, and there will also be an opportunity afterward to have more questions. So So let's get going. The goal of this is to try, exactly as the title explains, is to tell you, what frequency combs are and how they work. So the outline that I will proceed on is shown here. I first want to give you a little bit of background on how we got to where we are now. Like, why frequency combs, where did this technology even come from, okay? Then I'll discuss a little bit, different ways, and I call that the multiple faces of an optical frequency comb. So there are different pictures that might be useful to start developing in your mind as to what a frequency comb is. And then the bulk of the talk then will be talking about different classes of frequency combs and some of their basic operational principles. And I'll talk about mode-locked lasers, a very new and exciting technology, microcombs, and I will just briefly have time to mention electro-optic frequency combs. It's kind of interesting. They were some of the first combs that people were working on in the 90s, and now there's some new ideas that brings about a resurgence where they have some interesting properties for various applications as well. And then I'll just wrap up with some challenges and opportunities for the past. So the frequency comb really came out of an effort in the precision spectroscopy, the time and frequency community, to build better clocks. And this is kind of a long view of the progression of uncertainty in optical clocks. So down is better on this chart, and this is the clock uncertainty in seconds per day as a function of year. And so, there were pendulum clocks back in the 1600s that kept time to maybe, 10-second or second per day type scale. And as history progressed, there was a transition in about 1950 from mechanical clocks to atomic clocks. So the first cesium clock was around 1950, introduced in the NPL in the UK. And since then, there's been this very rapid improvement in clocks based on the atomic technology, down to where we start to now have optical clocks that are here at the bottom, even falling off the chart. It's hard to keep up with the progress. So there's been, in fact, a kind of a Moore's Law-like improvement. Maybe many of you know the semiconductor kind of scaling of transistors on a chip, about 1.5 decades per 10 years. Timekeeping is not too far behind. And in fact, it's been something that has progressed, as you see here, extremely rapidly. And where it ends up, no one quite knows. One thing that has been true through this history is that the frequency, the fundamental frequency of the clock has increased as we go to higher and higher precision or better performance, from kind of Hertz oscillators to tens of kilohertz with quartz. The cesium clocks, which are now the definition of the second, are kind of 10 gigahertz, and now optical clocks are in the 500 terahertz range. So if we wanted to project where this is going, perhaps it's going to be clocks that tick at petahertz in the future. Another interesting observation is that, a very important one, is that clocks have fueled some of the most important technical and even sociological or developments that really pushed our societies and our world forward, from enabling people to cross the Atlantic to scientific demonstrations of understanding that the Earth's rate is not constant. So there's geophysics, and there's astrophysics, and understanding the spin down rates of millisecond pulsars, which imply they're shedding gravitational waves. Down to GPS time, where maybe we get a little bit of the flavor of the Moore's Law scaling. There's probably 1 billion smartphones in the world right now that have GPS receivers, and that are guiding us, that we're being guided by clocks that are orbiting us right now. So there's much interesting physics and science, and I hope that these are some of the things that we want to try to work together to crystallize, what might be the next or new interesting developments that the technologies that we will talk about will enable. So this idea of using higher frequencies, that's really been the drive for optical clocks, or for atomic timekeeping. And there's a very simple scaling that if you want to think of a second as being ticks on a ruler, and if we divide up the second into, in the case of a microwave frequency, maybe 10 billion subdivisions, in the case of an optical frequency, we might be 100,000 times more precise just by the nature of the fact that the frequency of the optical light is about 100,000 times higher than the microwave. So this was something that one of our speakers, I don't see him here yet, John Hall, later in the week, it's really interesting. In the late 60s, early 70s, he already made lasers that were much more stable than microwave standards or microwave clocks. But there was no way to count or control or measure those optical frequencies. And that was really a hard problem for about 2 or 3 decades that no one had a good solution to until the late 1990s. And that is really where the frequency comb entered in as a tool to measure and count optical frequencies. So in the context of optical clocks, how does that work? Let me just briefly explain that. An optical clock is a clock that ticks at the frequency of a laser. It's actually the light wave, the crest and valley of that electromagnetic wave that are the pendulum, if you would, of the clock. And maybe this laser is first stabilized to an isolated cavity. It provides kind of a short-term reference. Atoms then, with an atomic resonance in the optical domain, or even the near UV, provide the stable, long-term accuracy of this clock. And now, as I showed in the previous slide, the level's kind of at part 10 to the 18, remarkable type of precision. So the last piece to come along was what I mentioned, this counter in the readout. And that is really the laser frequency comb. It's a way of counting and measuring optical cycles. At least that's, and I wanted to just make this point clear, is that's the way this field evolved, is starting with this tool as a counter for optical clocks. But as I hope to show, and I think Nate Newberry in the next talk will explain even better, is that now there's a wide range of applications that make use of this same basic technology. Okay, so let's talk about, kind of what I call the multiple faces of a frequency comb. Well, maybe the simplest picture is a frequency comb is just a ruler for light frequencies. Think of a ruler and cross out the millimeters or centimeters and put optical hertz on there. And that can be an absolute ruler traced to the definition of the second or of the hertz. In a frequency comb, this shows up as some broad optical spectrum. And if you can zoom in there, there's millions of little teeth, the teeth of the optical comb, the ticks on the ruler. Well, the Fourier transform properties tell us that if you have this in the frequency domain, then in the time domain you have a perfectly spaced train of optical pulses. And the properties of this pulse train are, of course, related. For example, the spacing of the teeth in the optical domain is inversely proportional to, or inversely related to, the time separation of the pulses. And the bandwidth of the optical spectrum, the total bandwidth, is related to the shortness of the pulses. So these are simple pictures that one might develop. Another picture that I really like is that the comb is an optical clockwork. It's a set of gears, okay? And I think this is a real powerful picture because it conveys the idea that a frequency comb is like a synthesizer. It's a tool that if you can enmesh and build together the right set of gears, you can synthesize frequencies, not only in the optical domain, but in the microwave domain as well. So it has incredible uncertainty. The teeth, if you will, on these gears are perfectly spaced and can be perfectly measured and controlled. And it can connect optical frequencies, as shown here, maybe these two, nu 1 and nu 2. And it also provides this down conversion, and this is the clock type application of allowing us to count optical frequencies relative to some microwave reference or transition. Okay, so that's maybe a few pictures that you can have in your mind as to what an optical frequency comb has, or what it looks like. So now let's shift gears and get a little more concrete and talk about actual, things that are, how do you realize these simpler pictures? So first I'll discuss mode-locked lasers. So mode-locked laser is a type of laser that produces short pulses. And here I've shown a simple kind of bow tie cavity. There's maybe some laser gain inside the cavity that's excited by, in this case, another optical source. And inside this cavity is something that's like a bullet, or maybe it's even a better picture as a pancake of light that's just circling around in this cavity, and each round trip there's maybe a partially transmissive mirror and a little bit leaks out. Okay, so this is kind of a simple picture of a laser. If one was able to stop that with a femtosecond scale camera and take a picture, this is what you would see, is that from pulse to pulse, here's the short bullet of light, and each pulse that comes out, first of all, they're exactly spaced by a number related to the round trip time in this cavity. But an interesting fact is that the envelope and the carrier, you note there's some slip, if you will, from pulse to pulse, where the carrier advances with respect to the envelope, and this is simply because the group velocity and the phase velocity inside this cavity are slightly different. We come back now to, and this is again two of these faces of the comb I already described to you. In the frequency domain, the Fourier transform of this is again our optical frequency comb, but now we get a real key piece here that's related to this carrier envelope phase slip, and that is that these teeth are not pure harmonics of the rate at which pulses come out, but rather are offset. If you extrapolate back to 0, there's an offset frequency, and that offset frequency is exactly related to this carrier envelope phase shift. So now we can write, with this little bit of knowledge, we can write the optical frequencies of this comb exactly as an integer times this mode spacing plus a common offset. And that's really the key concept and the equation that is most important to remember. There's a nice image that maybe for some of you who haven't seen how this the group and phase velocity relate. So here's a picture of a pulse evolving in a laser cavity. So maybe this is a high reflector. Now we got a linear cavity, and here's the output coupler in each round trip. Some light comes out, and as you can see that in the cavity where there's dispersive medium, this carrier envelope phase is evolving. Once we're out in free space, it stops evolving, or at least maybe there's only a constant shift, and so that a subsequent pulse that comes out, we'll see it here in just a second, has a different carrier envelope phase relative to the first one. And it's this periodic slipping of the phase relative to the envelope that again is related to that offset frequency. So let's tie this back in another way. Many of you know about cavities, or even acoustics, right? Acoustics is all about cavities as well. And so a frequency comb is, you can simply think of it as being composed of the multiple resonances, and these would be standing wave modes of an optical cavity. So here I'm depicting two mirrors, and these are just the plucked guitar string modes, or the lowest order standing wave modes that when locked in phase add up to give a short pulse at the output each round trip. And it's indeed these modes, and I show them displaced in space this way just so I can make the point that it's these discrete modes that are the modes of the frequency comb. So how does that work? Okay, so for some of you who might already be saying, well, look, I know something about modes and cavities, and they aren't perfectly harmonically related. And even in an optical instrument or an acoustic instrument, they aren't always harmonics of each other, or at least it's hard to get them that way. So there must be something else going on here, or something that really forces those to be uniform. And you're absolutely right. And what it is relates to kind of the fundamental way in which mode-locked lasers operate. Mode-locked lasers, not in addition to a cavity and some gain source, they require this balance of dispersion control and phase modulation, and coupled with some sort of power-dependent gain or loss. And I won't say a lot about that, but that's the mechanism that introduces the mode locking. But the important point to take away on this slide is that if you drew a simple cavity like this, you would write down that the ideal mode spacing is just the speed of light divided by twice the cavity length. Well, because you actually have air in there, or the coatings on the mirrors are not perfectly non-dispersive, the actual modes, at one end of the frequency spectrum, there may be a little more closely spaced. At the other end of the spectrum, they're a little more widely spaced from this C/2L. So this dispersion means that the cavity modes are not evenly spaced. However, and this is the really important thing, is that there's a nonlinear phase shift or phase modulation in the mode-locked laser that compensates or corrects for this, such that these modes can all be locked in phase and become perfectly uniformly spaced. And this is a concept, and I describe it here for mode lock lasers, but a little later I'll talk about microresonator combs. And there's actually a very similar type of operation that occurs there as well. So just the basic physics, again, to reiterate what's going on there, is there's a balance between dispersion and nonlinearity that makes this perfect frequency comb. Okay, so let's show a few examples of what these devices look like if you've never seen a comb. Maybe it's interesting to know that at least with titanium sapphire, you can make a tiny one. Here's this little bow tie cavity I showed before. And this one is just 3 centimeters round trip, such that it makes a 10 gigahertz frequency comb. Other ones with titanium sapphire can make directly from the cavity very broad spectra, octave spanning spectra in fact. And here's the envelope, but again, if you zoomed in there, spaced by a gigahertz in this case, would be this fine-tooth comb. Ti-sapphire is kind of the Cadillac of laser material, or at least in the US, maybe we say it's a Cadillac. It's really exceptional laser material for making very short pulse lasers. It has the drawback that it isn't so efficient, and it requires quite a bit of green pump energy to make it work. I wouldn't say that this type of technology is ruled out for applications outside the lab, but it has some particular engineering challenges, I think, that would have to be overcome. Another type of technology is based on erbium doped fiber, and you can make frequency combs out of these as well, an erbium doped fiber laser. And one nice thing about this technology is that it leverages kind of the multi-billion-dollar telecom industry and all the components that operate in the 1550 nanometer region of the spectrum. So these types of lasers operate, in some cases, the quietest ones on this property of nonlinear polarization rotation. I won't go into the details describing that, but they can be very compact, integrated piece of fiber. And from these devices, you can also get, and I'll tell you a little bit more about this octave spectrum and why that keeps coming up, but you can get very broad spectra out of these after you've additionally broadened them in some nonlinear fiber. My colleague Nate Newberry, who will speak after the break, he and his colleagues at NIST have developed a very robust polarization maintaining erbium fiber. And this is, I realize those might be some specific words for people who are outside the laser community, but essentially these lasers can now be made to be kind of a single piece of fiber, integrated fiber, no air gaps, just all continuous fiber, all the way out to amplifiers and nonlinear optics that are required for their frequency control. And Nate and colleagues have shown that you can put this type of laser in the back of a van and drive it around the hills behind our lab in Boulder. The good news, or I think a really exciting piece of news, is that not only are these things happening at national labs, but Ronald Holzwarth, who is president of Menlo Systems, will tell you about, or can tell you about, similar technology that is now available to even buy. So these are quite robust and becoming more and more widespread type of lasers that people are able to use outside the lab. I want to mention one other technology and just highlight, you can put different ions in silica fiber instead of erbium. Let's put ytterbium. And you can build lasers out of ytterbium fiber. I think the most interesting thing, and the point I want to make about ytterbium fiber lasers, is that they're incredibly scalable. Right now people have gone up to near 100 watts of 100 femtosecond pulses using this ytterbium fiber technology. In fact, I think you can get even, with ytterbium, what people will tell you in the laser field is the amount of power you can get out is essentially limited by the pump power. And so you start running out of laser diodes to pump this material before you run out of actual power that the system could support. So just before the meeting, Deborah Fisher, who's sitting here in front, said, well, what do you mean by optical frequency comb? So I want to address that comment right now. And I think, to be fair, that's a very good question. I think when we started this workshop, we didn't really, we said optical frequency comb, mainly because that was where this work had started. It started in the optical domain, maybe in the near infrared, 1.5 micron. I think really the key thing is that by optical we mean it's laser based. And whether those lasers operate, say in this region here, say 500 to 1,000, that's titanium sapphire. These are the three materials I just told you about. Ytterbium kind of around 1 micron, erbium fiber centered around 1550. Maybe we call these all optical. But the point I'd like to make in this slide is that based on these types of systems, we can expand to the ultraviolet or even to the mid and far infrared using other nonlinear optical tricks, either harmonic generation, where we would take the second or third or fourth harmonic of light centered, say, at 1 micron, or difference frequency generation, where we would take two sections of this comb and subtract their frequencies in a nonlinear optical process, and that puts us out, say, in the 2 to 10 micron region. So I think for the context of this workshop, it's very important not to limit ourselves just to these ideas and these materials. In fact, there are other materials and systems that people are talking about, and I think you'll hear some about that later today, that are directly producing combs, say, out in the mid-infrared. So back to this picture I had offered earlier about a frequency comb being a gear or a clockwork. I want to just spend a few minutes telling you, okay, so that maybe gives a nice picture you can have in your mind, but how does that actually work, right? I just showed you that we're actually talking about mode-locked lasers. How do these gears actually connect and work together? Let me say a few words about that. Well, in a frequency comb, I had already told you there's a very simple expression for describing the frequencies of the teeth of that comb, right? The nth tooth is just an n times the mode spacing or the repetition rate of this comb plus a constant offset. So to make this gear work whole, to enmesh the gears, to connect the gears, we have to be able to measure and control these two frequencies, the offset frequency and this repetition rate. So usually the offset frequency is the tricky one. That's the one that came last. And this is measured and controlled by a technique we call self-referencing, and here we need an octave span spectrum to do this easily. The repetition rate, or the mode spacing, is it's more of a microwave or a radio frequency that we can easily measure or detect. It's just the rate at which these pulses come out of the laser, and that might be a gigahertz or 100 megahertz for mode-locked lasers. Usually we can measure that more directly. In some of the cases, however, I'll talk about microcombs in just a few minutes, that frequency can be higher, and therefore it can be more challenging. So we can either connect it to a microwave source or measure it or relative to a microwave source, or in some cases relative to a CW laser. And the next slide I'll describe how that works. So here's the picture of the comb again. I put it on its side. You'll see why I do it that way. Just a minute. So each of these teeth of the comb you can think of as a CW laser, okay? And these, I have to break the axis here because there's a lot of cycles in a second. They're just streaming out of this laser frequency comb, and we can label them as I've done here. So if we have a comb that spans an octave, and that's a very important point, and we keep coming back to that because that gives us access to this offset frequency. We can take light on the red side of the spectrum and use a nonlinear optical material to double its frequency and interfere it with light on the blue side of the spectrum. And from this interference, we get directly this offset frequency. Okay? If we want to then control the mode spacing, the way we do this whenever we have an optical clock is we take another continuous wave laser, and this laser I label with the frequency nu0 or nu naught. That would be the frequency of, say, the atomic transition in the clock. We can take that laser and interfere it with one mode from the frequency comb and then feed back, that is, to control the mode spacing of this comb such that these crests and valleys, we make what we call a phase lock. This mode is forced to walk in march step with this reference laser. Now, I had explained a few slides back that these modes of this comb are all already phase locked together, tightly phase locked by this nonlinear mode locking mechanism, so that if we can control one mode, then we actually gain control of all of them, such that their superposition of these modes adds up to be this short pulse each round trip, okay? So this controlling of a single mode relative to a CW laser now fixes the rate at which the pulses come out. The offset frequency fixes this slip of the carrier relative, or the slip of the envelope relative to the phase each time. Here I drew it for simplicity that the offset frequency was 0, so each pulse is identical. So that shows how we can go from an optical reference to coherently synthesize a pulse train. In my gear picture, that would be engaging a gear at a high frequency, right, up in the optical domain, and using the comb to divide down to a microwave rate. But it's fully reversible. We can measure this repetition rate and engage or control the comb there and multiply up to produce coherent optical frequencies, or optical frequencies that are coherent with the microwave source. So that's a bit of a technical picture, but I just wanted to give you an idea of how this gear work actually operates. So I'd already discussed that having very broad spectra are quite important. Here's one case. This is the first case of how these broad spectra were first produced, and that was with what's called nonlinear or microstructured optical fiber. And this is technology from 2000 or so. It completely changed the game in this frequency comb business. And I mention it now, though, because the properties of those optical fibers are exactly the same as more advanced materials that people are using now. And let me say a few words about that. So this is a piece of optical fiber. It's glass or silica fiber. And you can see there's some sort of honeycomb-like structure that if you zoom in there's an arrangement of air holes around a defect, or a little strand of silica there in the center. And this would be the place where the light would be guided down the center of this fiber. Now the important aspect of this fiber is, or the construction in this way, is that first of all, the confinement, this group of air holes packed around this defect, the confinement of the light is very tight. In fact, the diameter here might be only a micron or so in diameter. So you restrict the light to propagate in a small volume. It pushes the intensity up. It turns on nonlinear optical effects. The other feature that is not immediately obvious here is that the arrangement of these air holes forms something like a photonic band gap. And in such a structure, you can tailor the dispersive properties or the waveguide properties of this longitudinal waveguide such that the dispersion is drastically changed from that of standard silica to something, in principle, whatever you would design it to be. And that's shown here is that in a standard optical fiber, and this is the dispersion in some units, this would be the dispersion of silica. In these microstructured fibers, you can move the dispersion from something that's very anomalous down to something that is normal or near zero at 800 nanometers in this case, or slightly anomalous, excuse me. It would be from very normal, excuse me, I said that wrong, down to something around 800 nanometers that's anomalous. So this engineering, if you would, of the waveguide allows us to change the dispersion properties of this waveguide. And the combination of this dispersion engineering and the tight confinement of light allows you to generate these very broad supercontinuous spectrums. So here's a picture of an input spectrum from, in this early days, a titanium sapphire laser, and the output spanning, many hundreds of nanometers, more than an octave. And this octave is precisely what's needed for this self-referencing. It also, as you might imagine, it gives you light at a lot of different colors, and maybe those are useful for other types of measurements. Here's a picture of kind of a family of spectra from different laser systems, ti-sapphire, erbium fiber, and ytterbium systems that show kind of the different types of octave spanning spectra that are achievable. The blue is ti-sapphire at 10 gigahertz. Here, I showed this spectra earlier. The gray one is 1 gigahertz ti-sapphire that's directly emitting a very broad spectra. Red is what one typically obtains from, say, ytterbium fiber with one of these ytterbium lasers with one of these nonlinear fibers, and the green is what can be attained with erbium fiber. You'll notice that these units here might be relevant. Power per mode, as the repetition rate goes up, here's 10 gigahertz, we can have even hundreds of microwatts to approaching a milliwatt per mode. As the repetition rate goes down, that energy, of course, has to be divided among many more modes, so the power per mode is lower. So that's something that will play into different applications of these combs. Let me just, very concrete example, show you how this offset frequency is measured. So let's imagine we had, for example, this spectrum here, this green one. We could take light at the red end of the spectrum, we send it through a nonlinear crystal, and we make a little bit of light around 1 micron, and we heterodyne it with that light. And this is how you would actually lay that out in the lab in kind of just, there's of course more sophisticated ways to lay that out, but I just wanted to point out, very simple. You generate the broad spectrum, you take the infrared portion, you frequency double, and you combine with the visible portion. And if you put that onto a photodetector, this is what you would see. You would first of all see the harmonics of the repetition rate. There's still pulsed light hitting this photodetector, but in between you would see this offset frequency and replicas of it, because we are heterodyning a comb against a comb, if you will. So you get many different replicas of it here in the microwave spectrum. So there's just, somewhat for the record, there's been a variety of different systems that have been self-referenced and frequency controlled in this manner, starting with titanium sapphire down to now more recently thulium fiber. And this is even a few years old, so there's probably a couple extras that I've missed. And I think the point I want to, perhaps one of the important points to make from this is, first of all, I tried to estimate kind of and give you an idea of what I call electrical to optical efficiency is. That's actually the wall plug efficiency. So that includes some assumed losses for power supplies and things like that. But if you just want to throw out rough numbers, the most efficient systems are actually, at this point, are ytterbium, 2 to 3%. Erbium is close, maybe a little less efficient. Here's what I mentioned early on, that, for example, titanium sapphire is significantly less efficient. So those kind of factors might play into things as we think about applications, as we think about what would it take to put something this in a remote site or even in space.
So by feeding the comb against another comb, what information comes out that is helpful for this application?
You mean as I explained in the previous slide? So yeah, that's the, let's see if I can go back here.
Scott, can you repeat the question for the video?
So the question was, by beating the comb against another comb, what useful information comes out? So I think Nathan Newberry will describe to you some types of measurements that you can make by heterodyning 2 independent combs, okay? 2 separate frequency combs. And I'll let him talk about that. In this case, what I wanted to try to tell you is that this is kind of a self-beating of the comb, okay? So we take the light from the infrared portion of the comb and we convert it to green light, and we heterodyne it with the green light that already existed there. So it's kind of like taking the 2 parts of the comb and folding it over and heterodyning it against itself. Okay. And I could write for you after or in the break the simple math that shows that when you do that, you directly obtain this offset frequency. That is, what is the global offset or shift of the frequency comb from being pure harmonics of the repetition rate? Let's chat a little bit more afterwards. I can draw some more pictures to explain that. Okay, so how's the time looking?
It's right there.
Oh, it's right there. Oh gosh, I got lots of time, 24 minutes. Okay, good. So I'm going to shift gears a little bit, and I spent a lot of time talking about mode lock lasers. That's the more established technology, and now I'm going to shift a bit and talk about microcombs. And some of the things that we like to try and make analogies between these 2 different kinds of combs, and there are some good analogies. For example, this general statement I already made that you have to have a balance of nonlinearity and dispersion in these types of systems. But some of the analogies don't apply, so we have to be a little bit careful, but the basic picture of the comb still applies for the microcombs, and it's really just a different way of generating them. And by the way, there'll be, for those involved in the workshop, there'll be much more discussion about microcombs, and many of the experts in this field will be, presenting ideas in their work as well. So here's kind of a global picture of where the microcomb fits into this. If you go back to my very first slides where I said, well, where does the frequency comb idea come from? So here's where the microcomb fits into that. If you went back, 30 years or 40 years at a place like NIST or some other national lab, people were trying to make something that was like a frequency comb. I mentioned that people already knew in the late 60s, early 70s that a laser could be much more stable and could be a much better metrology tool than a microwave oscillator. But no one knew how to connect that or to measure those optical cycles coming by at kind of a femtosecond rate, okay? So people made something that was called a frequency chain, and I could tell you more about that in the break if you wanted. There was this revolution around the year 2000 where, something that was kind of 100 square meters was taken down to a square meter, and now, the commercial versions are even smaller than that, kind of a laptop notebook size, okay? So this was a significant reduction in space, and not only that, but it actually could work, and could work everywhere, or, and now you can buy these things. So the vision for the future, and this is where microcombs fit in, is that, well, there's new ideas and new technologies that could allow us to take, what is kind of a breadboard, or, here I say it's a square meter, maybe it's a square foot, but it could go down another factor of 1,000 to 10,000 in size by using technologies related to microresonators and integrated photonics. So this could, I think, have the impact of enabling frequency combs to operate in practically any environment. Chip scale devices, they could be very inexpensive and mass produced. As I'll tell you, some of the technologies here are basically the same technologies that people use to make computer chips. So they could be lithographically patterned and printed and fabricated in that way. And as they get smaller and less expensive, perhaps they could just be widespread, or, so that they could go into a variety of sensing or communication or navigation instrumentation. So what is a microcomb and how does it work? I like this play on words. It's a kind of a tiny revolution. And these are some ideas that were hatched here in Pasadena, actually, in a group of Professor Vahala and Lut Maliki at that time at JPL, now at OE Waves, but really gained a foothold in the laboratory of Tobias Kippenberg in around the year 2006. And the idea is to make a frequency comb with a little microresonator. And here I'll show you more concrete pictures in a minute, but the idea is that one would couple light into the periphery of this microresonator, and the light would circulate around and around here, and you could go from a continuous wave, just a single frequency of light, into a comb. And the way that happens is via a nonlinear optical process called four-wave mixing. You can think of this in a photon picture as two photons that compose this input light as adding up and then breaking apart, being spontaneously generating then a photon of higher frequency and lower frequency, and those would be your first plus and minus sidebands here, for example. So energy is conserved, momentum is conserved via phase matching around this, and the line spacing of this comb is given by kind of the resonator diameter. So there were some really nice examples of this in the work of Tobias Kippenberg, now at the Federal Polytechnic Institute or University in Lausanne, Alex Gaeta's group in Cornell, and Lut Maliki and colleagues at OE Waves now. And these are just some examples of combs that could be produced in this way. And so you see the input light, the residual input light, and then this broad optical spectrum that can be produced. And so something is maybe to take note of here is that now we're talking maybe in some cases of comb spacing up to 850 gigahertz or even a terahertz, or down to 25 gigahertz. But that's determined by the size of this device, and these devices are kind of millimeter to micron scale. So just by nature of the fact that the devices are small, the mode spacing is going to be large. So one thing that we've learned in the intervening years is that a beautiful comb like that, it may look regularly spaced, but it's possible that it's not at all useful for metrology or this clockwork. It's too noisy. So there's really an important emphasis on understanding and controlling the noise processes in these microcombs that's critical. It's related to that is kind of asking yourself, and it was one of the pictures of the faces of the frequency comb I described to you earlier, is what's, okay, if that's the frequency domain picture, what's going on in the time domain? So in some cases, these combs can produce short pulses, just like a mode-locked laser. In other cases, they aren't necessarily short pulses. So here's real devices, so kind of a gallery, and it's a rapidly growing field, and lots of different materials and technologies are coming online daily, if not monthly. So I probably missed something, but I just wanted to give a kind of a snapshot gallery of different devices, ranging from waveguide integrated silicon nitride to devices that are, for example, the silica toroids and wedges are devices that are produced here at Caltech. The crystalline resonators is the work of OE Waves and has been picked up in other places. At NIST, we've developed some quartz type resonators, and then there's even materials like diamond and aluminum nitride that have their own interesting properties for making frequency combs, or making these resonators that can be used for frequency combs. So a lot of different systems, and a lot of different technologies that go in there. Some of the common key properties that we like for making frequency combs in these devices is that they have high Q. That means that light that gets trapped in a resonance, and some of these resonators, it's very clear. You could imagine the light, it's like a car going around the racetrack, right? Some of these others, it's maybe not as clear. For example, where's the resonator here? It's this little bulge, and it's a whispering gallery type resonator, and the light is, maybe you want to think of it, it's totally internally reflected as it bounces around the periphery, the circumference of this resonator. So some of these, it's better defined what the cavity is. Some it's, you have to get used to this concept of the whispering gallery mode to really understand that. But what's common to many of these, or all of these, is that you'd like to have high Q. And in the crystalline devices, it can be up to 10 to the 10 or so. In silica, it's maybe a billion or a few hundred million. Some of the more integrated devices, nitride and aluminum nitride, it's lower numbers, but still the high Q, the ability to store light in these resonators is important. The small mode volume means that we can confine the light tightly, and nonlinear optics can turn on with low powers. Okay? I'd already mentioned that kind of the mode spacing is given by the round trip time around one of these devices. Controllable dispersion. I had introduced this idea in the context of the microstructured fiber, where you could play with the waveguide properties by adjusting the diameter, the pitch, the spacing of these air holes. You can do similar things with these types of resonators by adjusting what the actual shape of the waveguide looks like. And that turns out to be very important, is to control the dispersion. And in some cases, you can see that these can be integrated into a chip scale package, some more obviously so than others. I think we'll hear more about these, at least those who are participating in the workshop in the next few days. Like I said, from some of the real experts and pioneers in the field. So let me come back to the kind of comb generation principle in these microresonators and distinguish it from what happens in a conventional mode-locked laser. So here on the right, let's start there with a mode-locked laser. It's just a different picture of what I showed you before, but it has kind of these main components. It has some gain medium, and here would be energy coming into the gain medium. Pump light, for example, that green light, maybe in the case of this Ti-sapphire laser or diode laser, or it could even be electrically excited gain. But this laser cavity has dispersion, so some balance of dispersion, and mind you, what also is occurring in this gain medium is the nonlinear phase shift I mentioned. It's very important. And some satchel absorption, something that favors the operation at high peak power rather than low average power. So in contrast, a microcomb has no storage, no energy storage in the gain medium. It's just a transparent dielectric material that has a nonlinear response, and we call that chi3. That's a response that leads to this four-wave mixing. So there's no energy storage in the gain. That's a big difference. There is the dispersion. So we have the dispersion and the nonlinearity in this system. And the other interesting distinction is that here the pump comes from the outside. Here the pump is actually an integral part of the comb and the cavity. So just to revisit the picture I showed you a few slides earlier, you can have the pump coming in, and you can have this four-wave mixing process where the pump generates sidebands like this. There's also the possibility for non-degenerate, where you would take two sidebands and mix them together. And this is just, you can just add and subtract the energy in these simple vector pictures here, and you could generate two new sidebands. So that's a very different mechanism for generating a comb than this laser-based or mode-lock laser-based system. And here again, I just highlight some of those features that I had just mentioned. So there's very beautiful nonlinear optics, very simple nonlinear optics in some ways that goes into the generation of these microcombs. So let me just back up again, and because motivate what I'm going to say in the next slide is that one would start with a pump wave, and okay, we aren't using a cavity made of discrete components now. We got to think back to a cavity that's just a continuous resonator. But that cavity has resonances, okay? And so the frequency at which we couple the light into the cavity is quite important. So in this slide, I'm going to try to explain that a little bit, is that this, the resonance, the optical resonance that you would couple the light into this cavity actually becomes distorted due to the nonlinearity in the cavity. And so maybe at low power, one would see this as actually being something that looks much more like a Lorentzian, the more familiar type cavity resonance that you'd have in an optical cavity. But because we have high circulating power and this nonlinearity, as the power goes up, the index of the material goes up and the resonance shifts. So as we bring the pump into resonance, the resonance actually moves away from the pump frequency a little bit. And so you have to keep moving if you want to come to the resonant peak, you have to move the pump laser with the resonance as it moves. This is called a Kerr nonlinear cavity, and it's described by this simple equation which has only 3 or 4 parameters. It has the strength of the field, that's the electric field squared, so that's the power. This term describes dispersion. This is the power of the pump, and importantly, it describes detuning, or where the pump sits relative to this cavity resonance. So there's a very simple equation that describes this, but the behavior can be quite complicated. And this is an example of the types of combs that are generated. For example, if you take the pump laser, that's the center frequency here, and scan it into the resonance, and we call this the upper level of this bistable type resonance, and you can see that you get, as you ramp up the power, you start with a very sparse comb, and then the comb can fill in and can fill in completely. The characteristic, though, on this upper branch is that the combs generally tend to be noisy, and one would ideally like to jump to this lower branch, or the other side of the resonance, where one can have these very low noise cavity solitons generated. And this is something that is just now being understood in this field, and how to repeatedly and efficiently generate single solitons or low noise microcomb states is something that's actually a very active topic of research right now. And there are some clear paths, but there are some paths that aren't so clear, I should say. And we'll have there's lots of experts, and even people here in Carrie's group and the other speakers who can tell you more about the details of doing that. But I just wanted to point out that it's a very simple system in some sense, but there's some very complicated and intricate nonlinear optics that needs to be carefully manipulated and carefully, what do I want to say? You have to have a very careful way of landing in these single soliton low noise states. If you can do that, or if you can achieve low noise microcombs, and I should just add one other statement, is that there's not all of the microcomb spectra that we've seen are single solitons. That's maybe the most kind of simple final solution here is a single soliton, but in other cases one can have multiple solitons in the cavity, or still different configurations that are still low noise but don't have this unique kind of hyperbolic secant spectra here. But with those kind of spectra, I just wanted to point out that even with an imperfect total understanding, we've still been able to demonstrate ability to control the frequency of these types of microcombs. In particular, to control the mode spacing, okay? So remember, if we're going to use the comb as gears, we have to not only measure and control this offset frequency, and I'll get to that in just a minute, but we have to control the mode spacing. So these are some ideas that we have introduced or used to control the mode spacing, and interestingly, kind of at the level of a part in 10 to the 15 at a second. So if we can make a low noise comb in a microresonator, we can control it at these interesting levels here. So one idea is to just apply mechanical pressure and squeeze the microresonator. So I like this picture not only because it shows how we implement that. There's a piezoelectric device that's squeezing this glass rod, but it also shows you how in a laboratory setup we can couple into these resonators. There's a tapered fiber, a piece of optical fiber that brings light up and just barely touches the resonator, and that's how light is coupled in. In other cases, we can, and this is an approach that's useful when the mode spacing or the resonator is very small, the mode spacing is large. We can introduce, using electro-optic techniques, combs, kind of inside the parametric comb is the blue one, and then after the comb we introduce an electro-optic modulator to kind of link, in this case, the 143 gigahertz comb teeth. It's a challenging number to measure electronically, but if we can kind of subdivide it using an electro-optic technique, we can get down to a way of controlling and measuring this 143 gigahertz or even larger. I'll show you in an example in a few minutes, these larger mode spacings, and again, thereby control the spacing of the microcomb itself.
Scott,
Yeah?
what's the major noise source that you're working against?
Yeah, that's a good question. If I back... Oh yeah, the question was, what's the major noise source that we're working against? The major noise source is that this parametric gain is very broadband, and it can turn on in all of the resonances in uncorrelated manner. Maybe this is one way to think about it, is that you can generate, you introduce light into one resonance, and you try to get this nice cascading of the energy out. Sometimes the energy that cascades out, it falls at a frequency that is not exactly harmonically related to the mode spectrum. So it's in a simple way, or in simple terms, this is really the main noise process that we're fighting against or trying to control, is to figure out a way to get these combs to really all phase lock together, all the individual elements, because kind of their natural tendency is to just go all on their own, all the different teeth.
I see. And for the mode spacing, what kind of mode spacing do you expect that you can get with microcombs? I think right now it's 100 gigahertz,
Yeah.
I've seen, but maybe, do you think it's arbitrary?
The question was what kind of mode spacing one could get with microcombs. I just back up that, it depends a lot on the devices. These types of devices are, anywhere from 10-ish gigahertz or even a few gigahertz, up to kind of terahertz. So it actually is quite complementary to laser combs. With a laser comb, it's hard to get a mode spacing much above a gigahertz. So with the microcomb, it turns on kind of at the few gigahertz or 10 gigahertz range up to hundreds of gigahertz or even a terahertz. So another technique that we've been experimenting with is to, and it addresses just what Deborah had asked, is maybe we can seed this parametric oscillator with a little bit of light that we already have controlled. And so instead of sending in pump light at just one frequency, we can modulate a little bit of light and put on some sidebands that would be close to matching the natural oscillation frequency of the microcavity, and thereby enforce its behavior, its low noise behavior on a uniform grid. And I won't say much more about that. I guess the main point I wanted to raise here is that we do have techniques to control the mode spacing of these microcombs at significant or levels of significantly low noise. Okay, but what about the offset frequency? And the next slides will just walk you through, some very recent experiments that ourselves and other groups, the group of Tobias Kippenberg, have been employing to try to measure the offset frequency of a microcomb. So I have to admit that in these slides, it will diverge from being micro, at least for the moment. We'll come back to it with a path that we think could make a self-reference microcomb, but for a moment I'm going to have to diverge. And there's kind of a generation of the microcomb. There's some nonlinear broadening, some phase control and amplification, and then nonlinear broadening. And let me just show you quickly kind of how that works. We can generate a microcomb, and this is one that I alluded to earlier, that it's we can make a low noise microcomb, but this is some sort of a multi-soliton-like state that doesn't have a single smooth spectra, but the comb in fact is phase locked, and we've verified that. So this can be a low noise comb. We have to do some spectral shaping and amplification. That's showing the field at different places. And finally we get to a high intensity short pulse that can then be used in a nonlinear optical fiber to generate this coveted octave spanning spectrum. So we can do this with a microcomb, and in fact can measure the offset frequency. So again, back to the question that was asked earlier, what we actually do is we take light from this side and we frequency double, and we heterodyne against light at this side. And if you zoom in here, and this line looks a little fuzzy, and that's because if you zoom in, you actually see with the relatively low resolution spectrometer that was used to make this measurement, you see the actual optical modes. And you can measure the offset frequency here. It's the spacing of the modes between the doubled and the original comb light. And if you put that on a photodetector, you actually see this offset frequency of the comb. And the good news is that it can be quite narrow and low noise and controlled. So I told you I was going to mention electro-optic combs. Just one brief word about that. Those in the workshop will hear more about this from Scott Papp. But I wanted to just mention that not only did we learn the nonlinear optics here that enabled this, but this is a way of starting with a CW laser without a microresonator to grow up octave spanning combs. So I apologize, I won't have time to go into that now. But I wanted to now just wrap up by coming back to this idea of, I showed you a way we can self-reference this, but this is, here's the micro, and this is all pretty macro. So it teaches us something to understand how these microcombs work and how they can be controlled, but we would like to think ahead of a route, how could that all be integrated? And here's one possibility, and this is something that ourselves and people at Caltech and Santa Barbara and in Europe are working on together. And the idea is the goal is to ultimately have this octave spanning self-reference comb on a chip. The challenge is the power constraints. How do we do this with low power and with basic nonlinear optics? The idea from the gear picture is we're going to have a dual reduction gear. I see the red light blinking, huh? Okay, so I'll talk fast here. But we're going to first go from 200 terahertz, the optical frequency, down to a terahertz, and then to 15 gigahertz eventually. So it's kind of a nested gear approach where we're going to use different technologies, silicon nitride to make the terahertz comb, and silica to make this 15 gigahertz comb. So let me just say a few words about this terahertz comb generator. here's a zoom in of the kind of rings that our colleague Kartik Srinivasan at NIST in Gaithersburg has made. And some of the important things that we have to understand about that is how to control the dispersion and how that dispersion couples to the nonlinearity to make spectra that start to become octave spanning. So these are models, okay, and calculations. I have to talk quickly here at the end just to run over this, but to show that now for the first time in this terahertz comb generator, with what I think the most exciting point is it starts to be a relatively modest amount of power, just a few hundred milliwatts, we can make this octave span comb. And moreover, this power required scales as the quality factor of this resonator. So we think there's good reason to believe this could be even a factor of 4 or 5 lower. So I think, where this is going, I think with microcombs, there really is a vision that all of this could be integrated on a kind of chip, and with not only with electronics and pump lasers and active components, but the full gear work, if you would, the clockwork that would enable the optical to microwave conversion. Okay, I will just wrap up quickly. I think I'll skip that slide. What I've described to you is combs that are useful for clocks, or at least I started there, but there are many applications of frequency combs, and our next speaker, Nate Newberry, will go into that. I just wanted to point out that maybe some of these applications best use a mode-locked laser comb, maybe some of them use a microcomb, and that will be interesting things to debate and discuss with everyone here. Finally, just some last slide on challenges and opportunities. There really are gaps in our knowledge. You even heard me not be able to say, so sharply how it is that we can make low noise states in a microcomb, because we know paths to do this, but there's still incomplete knowledge there. And so we need to learn about that. Fiber combs, in many cases the technology is mature, but it still employs some empirical recipes. The technology of all of these devices is complex. We need improved robustness, spaceworthiness if it's going to fly. There's a lot to be understood about materials and systems, not only for the nonlinear optics, for generating new colors in the mid-infrared, or new materials are coming online. What's going to be the best platform to achieve different wavelengths, to achieve combs in different wavelength regions. There's of course the question of integration, and then matching the technology to the application. So I will stop there. I want to thank, these are at least a snapshot of some of the people who work with me in Boulder. A lot of contributions there, and also for material I presented from colleagues here at Caltech and around the world who we work with. So I apologize for taking a few extra minutes, but we'll stop now, and thank you for your attention, and happy to answer any questions.